Okay, next. So R and Cn are complete space with a Euclidean norm. That is what we are going to prove. So Euclidean norm, you know that norm 2, right? So we have to show that it is a Banach space. It is similarly Cn. That xp is a Cauchy sequence in Rn. So therefore by definition what you have, norm of xp minus xq is less than epsilon for all pq greater than n. n ഉപയോഗിക്കുന്നത് ആർ എന്നുള്ളത് ഇട്ടുകൊണ്ടാണ്. So norm 2 ആവുമ്പോൾ how you will define norm 2, sigma I equal to 1 to n modulus of xp of I minus xq of I whole square whole raised to 1 by 2. pth norm ആണ് whole raised to p whole raised to 1 by p അല്ലേ കൊടുക്കുക. അതേപോലെ less than epsilon for all pq greater than n, which implies sigma. So what you have is sigma 1 a modulus of xp of I minus xq of I whole square less than epsilon square. ഇവിടെ whole square 1 by 2 ആണ് for all pq. That's for which implies modulus of xp of I minus xq of I is less than epsilon for all pq greater than n. So what happens, xp of I is a Cauchy sequence in R with respectively in C. So therefore there exists some alpha I such that xp of I is tends to alpha of I, right? So let's take x equal to some alpha 1, alpha 2, etc. alpha n, which belongs to R of Rn. We have letting p tends to infinity, or p tends to infinity, what will get sigma I equal to 1 to infinity modulus of alpha I, right, minus xq of I whole square is less than or equal to epsilon square for all n for all m greater than or equal to n. Since n tends to infinity, so this becomes alpha I. So what you will have, less than or equal to epsilon square. So what do you get, norm of what is this, alpha 1 alpha x ആണ്. So norm of x minus xq norm 2 is less than or equal to epsilon for all m greater than or equal to n. Not m, actually it's q, right? Q q ആണ്, q greater than or equal to n. This is q greater than or equal to n, which implies what we are getting, this sequence is equal to limit of that sequence is equal to x, right? So that means that sequence converges in Rn. So with respect to Euclidean norm, that is norm 2, this is a Banach space. Similarly you can prove for norm p also. Otherwise you can write it's equivalent ആണ്. So norm p also with respect to norm p also is a Banach space. Okay, next consider another example. Set of all continuous functions on closed interval 0, 1. Okay, generally if you want you can write it as C of a comma b. Okay, clearly we know that it's a complete normal space with respect to sup norm. We have to prove that it is a complete space. That is we have to prove that it is Banach space. Let's suppose fk be a Cauchy sequence in C of closed interval 0, 1. For a given epsilon greater than 0, what do you have? There exists some capital N such that sup norm of sup norm, that is norm means sup norm ആണ് ഇവിടെ. So modulus of fn x minus fmx is less than epsilon for all n comma m greater than capital N. Okay, അതുകൊണ്ട് എന്ത് വരും, ഈച്ച് മാക്സിമം തന്നെ ലെസ് ദാൻ എപ്സിലോൺ ആയതുകൊണ്ട് what do you have, modulus of fn x minus fmx itself less than epsilon. അതുകൊണ്ട് എന്ത് കിട്ടി, the sequence fk of x, okay, clearly is a Cauchy sequence for each x. ഓരോ x എടുക്കാലും f1 of x, f2 x, f of f3 of x, etc. is a Cauchy sequence. Okay, so clearly that converges for each fixed x belongs to closed interval 0, 1. How? Each fk of x is a Cauchy sequence. എവിടെയുള്ളതാ, each fk of x is actually is a continuous function on this one. So it's on R, right? So clearly it converges. Therefore let's suppose f of x is equal to limit x tends to infinity k sum to infinity fk of x. Okay, so now what you have to prove, ഈ f of x ഇവിടെ കിടക്കുന്നുണ്ട് എന്ന് കാണിക്കണം, റൈറ്റ്? എന്നാലല്ലേ കാര്യമുള്ളൂ. ഓരോരുത്തരും കൺവേർജ് ചെയ്യേണ്ടതെന്ന് അറിയാം, മനസ്സിലായി. ബട്ട് ഇത് ഇവിടെ കിടക്കുന്നുണ്ട് എന്ന് കാണിക്കണം ഓരോ f of xകളും. fk is, we need to show that fk tends to f uniformly. You have to prove that fk is tends to f uniformly. Uniformly converge ചെയ്യുമ്പോൾ എന്താവും, ഈ f എവിടെ കിടക്കും, uniformly converge ചെയ്യുകയാണെങ്കിൽ uniform that limit is also continuous, right? Continuous functions uniformly converge ചെയ്യുകയാണെങ്കിൽ അതിൻ്റെ ലിമിറ്റും എന്താ തന്നെയായിരിക്കും, continuous ആയിരിക്കും, right? So that is what you have to prove. Now let's suppose for every x epsilon we have, for every x belongs to closed interval 0 1, we have modulus of fn x minus fm x is less than epsilon for all n comma m greater than or equal to n, right? We have this one. ഓരോരുത്തർക്കും ഇത് സംഭവിക്കുന്നത് ബൈ ദിസ് കണ്ടീഷൻ, റൈറ്റ്? ഇത് ഈസ് ഇറ്റ് എക്സ് ഡിപ്പെൻഡിങ് ഓൺ എൻ എന്ന് പറയുന്നത് എക്സിനെ ഡിപ്പെൻഡ് ചെയ്യുന്നുണ്ടോ? ഇല്ല. n does not depending on x, right? Now let us suppose m tends to infinity. M tends to infinity, we know that each fk is converges to f1. So we have modulus of fn x minus f of x is less than epsilon for all n greater than or equal to n. Okay. Here also x does not depend, n does not depending on x. അപ്പോൾ എന്താർത്ഥം? യൂണിഫോം ആയിട്ടാണ് കൺവേർജ്, റൈറ്റ്? സോ ദാറ്റ്ഫോർ വാട്ട് യു ഹാവ് supremum of x belongs to modulus of x minus fn x of f is less than epsilon for all n greater than or equal to capital. That is what you will have, what you have, fn converges uniformly to f, right? fn converges uniformly to, that is, what is this one? Norm of fn minus f. What is this? Subnorm, ഇത് എഴുതിയിരിക്കുന്ന norm ആണ്. Norm of fn minus f less than epsilon for all n greater than or equal to capital N. Okay. That is, therefore fn converges to f uniformly, okay, uniformly on closed interval 0 comma 1, okay, otherwise a comma p. So what do you have? fn പറയുന്നത് കണ്ടിന്യൂസ് ഫങ്ഷൻസുകളാണ്, അത് കൺവേർജസ് ടു എഫ് യൂണിഫോംലി ആണ്. അങ്ങനെയാണെങ്കിൽ ആ ലിമിറ്റും യൂണിഫോം ലിമിറ്റും എന്ത് തന്നെയാണ്? കണ്ടിന്യൂസ് ആണ്. സോ എഫ് അഗെയിൻ ബിലോങ്സ് ടു വേർ യു ബിലോങ്സ്, ഇറ്റ് വിൽ ബിലോങ്സ് ടു ദിസ്. therefore completeness of f follows from the fact that uniform limit of a sequence of continuous function is still continuous. So f belongs to that space, so becomes f is also becomes complete. Okay, so we will go for another examples in the next part. ഇനി ധാരാളം എക്സാമ്പിൾസുകൾ നോക്കാം, അടുത്ത പാർട്ടിൽ നമുക്കത് നോക്കാം. ഓക്കെ, താങ്ക് യു.